2020 E&M, new problem number 3. This is another circuit, and this time they've given us a graph of charge versus time and a horizontal asymptote at 20 coulombs and an initial slope of the tangent line at time t equal to 0 such that it crosses at 20 coulombs and 2 seconds. All right. For part A, we're going to suggest values for V, R, and C that'll produce this graph. All right, so on this graph, we can get the current by the initial current anyway, by dividing charge divided by time. So for part A, current is going to be Q over time, which is going to be 20 coulombs over 2 seconds. So the initial current is going to be 10 amps, which also should be the voltage divided by the resistance, because at time t equal to 0, the capacitor is uncharged. So we need to have our voltage and our current voltage and our resistance divided 10 amps. Now we also have a final charge of 20 coulombs. So Q equals VC. These guys need to be equal to, I don't know, I did an arrow there. These guys need to be equal to 20 coulombs when we're all done. So whatever numbers we pick need to obey those rules. So if we pick, let's start at the bottom and work our way up. If we pick 200 ohms for this guy, oh, and one more thing, this also indicates that our time constant should be 2 seconds. And we can get that by combining these two equations. So 10 amps is V over R, and then if we rearrange this so that V is 10R, that's a 10, and then we plug that into here, we're going to have 20 equals 10 RC, so then RC equals 2 seconds. That's our time constant here. So when we do 200 times C, we need to get 2. That will produce a capacitance of 0.01, and that'll be farads. Now let's see about C. What are we going to, the voltage, what are we going to get for the voltage here? So we need to have a voltage divided by 200 is 10. Well, that would be 2000. Does that agree with our rule here? So 2000 times 0.01, move the decimal place 2 places, that'll get us 20. So 2000 times 0.01 gets us 20, that's expected. 2000 divided by 200, that gets us 10 amps. And then 200 times 0.01 satisfies 2 seconds. So as long as your values obey those 3 rules, you can pick any numbers you want. They just have to multiply or divide to be 20, 2, and 10. All right, part B. What we want is for the capacitor to charge up twice as fast. So what we want is RC to be 1 second. So we need the thing on the left to be cut in half. But at the same time, they say we want the same horizontal asymptote. So we want the same charge. All right, so we want Q equals VC to stay the same, but we want RC to be half as much. So this indicates that we need to mess with R. And we need to mess with R by cutting R in half. And the way you reduce resistance is by adding a resistor in parallel. So 1 over R total is going to be 1 over R plus another 1 over R, which gets us 2 over R. So when we flip these guys upside down, our total is going to be R over 2. Now when we do that, we plug that puppy into here. R over 2, that will cut this into 1 second. And notice how there are no R's in Q equals VC. So messing with the resistance is not going to mess with the overall charge that we put onto the capacitor, so we will have the same horizontal asymptote. So we're going to need to add resistor in parallel. Make our total 1/2 of original. QVC does not depend on R. No change in Q. Having the resistance, which is this guy, so I equals V over R total. Initial slope will be twice as much. Notice how if we change the battery or the capacitor, we're going to end up changing the charge on the capacitor. And we don't want to change the charge on the capacitor at all. All right, part C. We take a look at this power function. We started at 0, power being delivered, increases to a maximum, and then decreases asymptotically back towards 0. So explain why the graph starts at 0, goes to a maximum, and then reaches 0 again. So we've got 3 things to account for. And I'm going to need to clear out this guy and reopen it. So for part C, power being delivered to a capacitor, I would use P equals IV because we don't care about the resistor. What we care about is the capacitor. And the equations for a capacitor is for I, that's going to be I naught e to the minus T over RC. And for the voltage, this is going to be V naught, and that'll be 1 minus E to the minus T over RC. So the initial current, well, when you plug in 0, that's going to be a maximum, but the voltage is at a 0. So 1 minus, well, this will be 1, that gets a 0. So P naught is equal to 0. Because V of 0 is equal to, and this V naught is, that's the max. V of 0 is equal to 0 when cap initially uncharged. So that's important point number 1. Important point number 2, reaches a maximum. Power delivered to cap is non-zero when there is still some current, because that current is going to be exponentially decaying right here. The current is always going to be exponentially decaying, so there's going to be some time in between the maximum and 0. So there's still some current, but voltage no longer 0. So while this is not yet 0 and this is stopped being 0, that's when you're going to get some non-zero power. And that's the whole point of this maximum point right here. Okay, and then asymptotically reaches 0 again because the current is exponentially decaying. Current goes to 0. So that means the power will also go to 0. All right, part D, and accidentally swiped there. All right, now for part D, we somehow managed to overcharge the capacitor. So now the capacitor, if we hook up a voltmeter here, is equal to 2V. this voltmeter, this capacitor is now overcharged. And what's going to happen is it's going to push charge backwards into the battery until these two voltages are equal. So let's see here. Describe how the graph of charge versus time from part C, there was no graph, they must mean part A. This has got to be a typo. Would appear now the switch is closed. Be sure to address the initial slope and final asymptote. Okay, so charge will move backwards into battery until voltage of battery equals the voltage of capacitor. So it'll be the same slope as before, but negative, because it's going the opposite direction. So that's important point number one. The final asymptote comes when the voltages are equal. So we will have the same asymptote at Q equals 20 coulombs as before, but it will be approached from above, whereas before it was being approached from below. So if you take a look at this, the asymptote is being approached from below. Now our graph is going to start here, and it's going to go through here and then reach that asymptote. Let's see how well this goes. Essentially, what we want is for it to be mirrored about the asymptote. Graph will be mirrored over the horizontal asymptote.